In this lecture, we will be talking about air pressure and how winds are created. We will start with a review on high and low air pressures, and then we'll move into talking about the pressure gradient force, the Coriolis force, the difference between surface and upper level winds, and we'll also talk about troughs and ridges. Let's start with air pressure. As we know, air pressure is the amount of air above the surface of a specific location. And the differences between air pressure is based on temperature. So the colder the temperature, the more the air slows down and sinks, and it exerts more pressure on the surface, thus a high pressure. The warmer the air, the more the air spreads out and exerts less pressure at the surface, resulting in a low pressure. We measure air pressure using a barometer, and therefore when we talk about air pressure, this can also be referred to as barometric pressure. And as you recall, low pressure often results in rising air, clouds forming, and storms. High pressure is descending air and fair weather because we don't have that air rising to form clouds and storms. So you can see on the image on the right here, this is different barometric pressures that have occurred throughout history, and I've added a few with the hurricanes. Our standard sea level pressure, as we know, is 1013 millibars. So you can see down in the bottom part of the image here, we have a lot of low pressure situations. And these are often hurricanes and typhoons, so big storms. You can see Hurricane Laura from September 2020, 959 millibars was the lowest pressure at the inside of that storm. And Hurricane Dorian, 911 millibars back in 2019, was the lowest pressure inside of the core of that storm. Whereas you get to the high pressure here, you're talking about just high pressure and clear weather. So you're not seeing a lot of storms going on above sea level pressure. So one thing to note is that air on the surface always flows from high pressure to low pressure. Any low pressure system is also called a cyclone. So you've probably heard of hurricanes also being referred to as tropical cyclones. It's the same thing. A hurricane is a low pressure system. It's a big storm. When these systems, these big low pressure systems like you're seeing on the map here, occur outside of the tropics, it's called an extratropical cyclone or a mid-latitude cyclone. These are low pressure systems that are forming in the mid-latitudes. And we will talk a lot about mid-latitude cyclones when we start talking about frontal systems. When we are looking at high pressure systems, this is just the opposite. So we call it an anticyclone. On a weather map, you can read pressure using isobars. So isobars are lines of equal pressure. On the map on the right here, all the pressure along this line is all going to be 948 millibars. So everywhere around that line has an equal pressure. If you're familiar with topographic maps, isobars are very similar to contour lines. So we're going to move into how air pressure affects winds. At the surface, so we're talking just the Earth's surface, winds are affected by three things. The first thing is pressure differences, or what we'll call the pressure gradient force. The second is the spin of the Earth, or Coriolis force. And third, the frictional drag of the wind against the Earth's surface. Let's start with pressure gradient force. So the pressure gradient force is the movement of air because of a difference in pressure. And this movement of air is what results in wind. We know on the surface our air is moving from high to low pressure. And as you can see on the image here, that's what's happening. It's moving from this high pressure on the left, 120 millibars, over to low pressure on the right, 1016 millibars. And the pressure gradient force, or how strong the pressure gradient force, depends on how strong of a difference in pressure you have over the distance you're covering. So the more that pressure changes over space, the stronger or faster the wind will be. On surface maps, the closer the isobaric lines are, the faster the pressure is changing and thus the faster the wind speed. The farther apart the lines are, the slower the pressure is changing and thus the slower the wind speed. So for instance, on the surface map, we'd likely say this location here would have the fastest wind speeds on this map. We're moving from about 968 millibars to about 943 millibars as the air is traveling in towards the low, and this is happening over a pretty small space. We'd likely say this location here would have a slower wind speed, and this is because we're only changing from about 988 millibars to about 980 millibars as we head into the low pressure system, and this is happening over a pretty large space. So the pressure isn't changing very fast, and it's not changing very fast over a large space, and thus winds just aren't going to blow as fast. On a map like this, you can tell the wind speed based on this the symbol on these maps. So when we're talking about this real fast wind speed over here, we're talking about winds that are anywhere between 55 and 77 miles per hour, based on the symbols on the map. When we're talking about these slower wind speeds, we're talking more like 21 to 25 mile per hour winds. So much slower, much more gentle of a pressure change. So just a reminder, at the Earth's surface, air is flowing straight into a low, and at the Earth's surface, air is flowing out of a high pressure. Winds are also influenced by what's called the Coriolis force. So the Coriolis force is the apparent deflection of wind caused by the Earth's rotation. It's important to note that wind doesn't just take a right or left turn, it just seems like it's taking a turn because the Earth is circular and it's rotating. So let's look at this a little bit more detail. Earth is wider at the center than it is at the poles, as we know. All this air must travel in a full circle once per day. So the equator is spinning much faster than the poles. So you can imagine if you're standing on the poles, on the North Pole, for instance, and you have to make a full circle every day, you might just turn in a circle. Versus if you're at the equator, you have to go a very long distance to make a full circle on the Earth the entire day. This difference in rotational speeds is what makes the winds seem as though they are bending. The deflection is greatest at the poles and almost negligible at the equator. And the faster your wind speed is, the more Coriolis will influence the deflection of your winds. Coriolis causes a deflection to the right in the northern hemisphere and to the left in the southern hemisphere. And this deflection is based on where the air is coming from and where it's flowing to. So for instance, when we're looking at the southern hemisphere here, if we are starting and standing right on this location and looking towards the south, our air would look like it's deflecting to the left, even though when we look at this just straight on, it looks like it's deflecting to the right. You have to almost position yourself on the Earth and look at where the wind is going to be able to understand where that deflection is happening. And we'll work on this a lot more when we start talking about global winds. In the left image, you can see the intended path of a plane as it is flying from one point to another. The idea is that you could fly along the line of longitude. However, because of Coriolis, planes flying from west to east in the northern hemisphere see a deflection to the right. And again, the deflection is strongest at the poles because of the curvature and the rotation of the Earth, and almost negligible at the equator. And one point I'd just like to make is that we will generally be discussing the northern hemisphere from here on out. And if we ever are talking about the southern hemisphere instead, I will note that. When we start to combine the pressure gradient force and the Coriolis force, we find that they balance each other out and cause air to spin around a pressure system. So in this case, the red arrows are the pressure gradient force, which is more influential, And that's what causes air to flow into a high and out of a low. And then we have green arrows, which are the Coriolis force, which cause the air to deflect in the opposite direction as a pressure gradient force. So that ends up causing more of a spin of the airflow. And with a low pressure system, we see a counterclockwise spin. And with the high pressure system, we see a clockwise spin. At the Earth's surface, friction also has an influence on the wind. So as the wind moves over the Earth's surface, friction will slow that wind down and it lowers the Coriolis effect. So when we combine all three forces at work here, this is what we end up with. Again, the red arrows are the pressure gradient force, which is the most influential, and it causes air to flow into a low pressure and out of a high pressure. Coriolis, the green arrows, pull the air in the opposite direction. That's what's causing that deflection. And then at the surface, friction slows the entire process down. The combination of all three forces results in airflow like you are seeing with the blue arrows here. So air flows into the low pressure system in a gentle counterclockwise pattern and out of a high pressure system in a gentle clockwise pattern. When we talk about wind aloft, so this is air that's above the boundary layer, it's no longer affected by the frictional drag of wind and the earth. Winds are only affected by the pressure gradient difference and the Coriolis force. And again, we have this cyclonic or counterclockwise flow around a low pressure system. And we have this inward directed pressure gradient force being balanced by the outward directed Coriolis force. And this results in just a spin around a low pressure system. The opposite is true for the high pressure system. So we have this clockwise flow, and the pressure gradient force is pulling the air out of a high pressure system, but this is being balanced by the inward directed Coriolis force. And so we just end up with a clockwise spin around a high pressure system. When we talk about these winds aloft that are above the boundary layer, we idealize them and call them geostrophic winds. So those geostrophic winds actually blow parallel to isobars. And you can see that happening on the top image on the right here. So what's actually happening is that we know that winds are affected by the pressure gradient force, and this is still more influential. And it's also being deflected by the Coriolis force in the opposite direction. And this results in that wind that blows parallel to the isobars. So remember, it's not being slowed down by friction in this location of the atmosphere, and thus it can just blow parallel to isobars. So that idealization of winds is geostrophic winds. The actual flow of air aloft is called a gradient wind. On upper level maps, we often see lines of equal temperatures. These are called isotherms. They are the red lines that are shown here on the map. So these isotherms tend to follow the same pattern as our isobars, our lines of equal pressure. And that should be fairly obvious because we know that pressure changes result from temperature changes. So our air here is having these big swooping bends because of temperature, pressure gradient force, and Coriolis. And of course, we know we have cold air to the north and warm air to the south. So what we end up having happen is troughs or very elongated lows, as we're seeing on the left here. And this is cold air that's sinking downward on the Earth's surface. It's sinking from the north towards the south. We also have ridges, which are elongated highs. And that's warm air rising from the south going towards the north. Even with these ridges and troughs, and you can see a big trough here, our airflow, our winds are still flowing parallel to the isobars aloft. And so these flags here are showing you the direction of the wind flow. And it's basically taking you right along with parallel to those isobars. What we end up seeing is the difference between surface winds and upper level winds. As we just mentioned, our upper level winds are following the pattern of the isobars. But because we have frictional influence on our surface winds over here on the left, our winds are actually flowing perpendicular to the isobars. So again, at the surface, what we're looking at on the left here, our winds are blowing across the isobars because of frictional influence. And that's why you're seeing these arrows go across the isobars instead of along with them. In the upper level map over here on the right, we have those gradient winds, and those winds are blowing parallel to the isobars because this is above the level of frictional influence. So friction isn't slowing that air down. So again, you just have that air flowing parallel to the isobars. In the southern hemisphere, you have the exact opposite situation. Air is still flowing into a low and out of a high, but they are spinning in opposite directions than in the northern hemisphere. So remember, this is because the Coriolis force deflects winds to the left in the southern hemisphere. So here, air circulates clockwise into a low pressure system, as you're seeing here on the right, and it flows counterclockwise out of a high pressure system, as you're seeing here on the right upper image. We describe wind based on where it's coming from. So wind flowing from the north to the south is a northerly wind. If we look at this upper air map over on the right here, we can look at this arrow here. It's coming from the south and it's heading to the north, thus we'd call it a southerly wind. This arrow over here is coming from the west going to the east, so we'd call it a westerly wind. And there can be any variations on this. So for instance, this arrow here is coming from the north, northeast, going to the south, southwest, so we'd call it a northeasterly wind. It always depends on where the air is coming from. We've been talking a lot about horizontal air movement or advection. We can also talk about vertical air movements. So air isn't just spinning at the surface or just spinning aloft. This air movement between the surface and aloft is connected. We know at the surface when we have rising air, this results in a low pressure system. This means we have warm air at the surface that's rising. However, aloft above a low pressure system is colder air. And you actually end up with a high pressure system aloft when you have a low pressure system at the surface. The opposite is true with high pressure systems. So at the surface, we have descending air and colder air at the surface with a high pressure system. However, aloft above the high pressure system, we have warm air and low pressure. And remember, air always flows from high pressure to low pressure. So it ends up looking like this. At the surface, over on the far left here, we have converging air, so air coming into a low pressure system. It comes together, it rises, and it starts to diverge up aloft. That air then moves from a high pressure up here, so this would be a high pressure. It's moving over to a low pressure. That air converges or comes together. It's cooling and it's sinking. As it sinks, we then have a high pressure system at the surface. And at the surface, that air has to go somewhere, so it diverges away from itself. Let's walk through this step by step to make sure we understand this process. So we're going to start at the lower left with this low pressure at the surface. And with low pressures, we always have convergence. So in this case, we have convergence at the surface. We have warming air, and thus when the air is warmed, it starts to rise. And as we know, as that air rises, it cools, and it can potentially reach the lifting condensation level or dew point. If it continues to rise, we know that can form clouds, showers, storms, and so forth. So this means we have cooler air aloft and thus a high pressure aloft. So again, it's that idea that we have a low pressure at the surface, but aloft we have a high pressure. And with high pressure, we always have diverging air. That air is flowing out of the high. So in this case, we have divergence aloft because we have cooling. And then we know our air is flowing from high pressure to low pressure because air flows into a low pressure. So as you can see here, we have convergence aloft. That cool air is now coming together and starting to sink. So we have that cooling. Then we have sinking air. And when we have a low pressure at the aloft, we have a high pressure at the surface. And when that air hits the surface, it has to go somewhere, so it diverges. Again, our high pressure sends air to low pressures, and it'll go in either direction. So you can see in this case, we can go all the way back to this original low, or it can head to this other low on the right. So when we have air then converge again at a low pressure, the same situation happens. Convergence at the surface, warming, and rising air. Above the low pressure, we have a high pressure because that air is cooling. It is now more dense. And then again, air is diverging aloft.